Namaste students, welcome to physics class. According to Oersted, you learned already current carrying conductor produces magnetic field. Through Oersted experiment, we analyzed and we got the information. Now, the converse. So, according to Oersted, current carrying conductor producing magnetic field. Now, reverse means can magnetic field produce current? That we are going to learn in electromagnetic induction lesson. Before going to the introduction to electromagnetic induction, first, one question for you. Can we produce magnetic field with current? The answer is yes. We already learned in the last lesson, that is one of the topic, Oersted experiment. So Oersted identified first the current carrying conductor produces magnetic field. So I will give the details in the next slide. So one more question. So here magnetic field produced by the current means current producing magnetic field. Reverse, can we produce current using magnetic field? That is also possible. So with electromagnetic induction. So before going to the electromagnetic induction introduction, so let me give the clarity about the current carrying conductor producing magnetic field, that is Oersted experiment. According to Oersted experiment, unfortunately it happened, Oersted one day in the laboratory near the current carrying conductor he placed one deflection magnetometer, then suddenly observed the deflection in the magnetometer. So with respect to that, he discovered one thing, that is magnetic field is associated with an electric current. It was discovered at that time. So if you discuss in a particular systematic way, so for that purpose just consider AB a current carrying conductor. So I found that when a wire AB carrying current was held over a magnetic needle NS, as shown in the figure, such that electric current passes from one end to the other end, then the north pole of the magnet got deflected towards the west. So here what it may be the direction. So simply one thing we can say, the current carrying conductor produces magnetic field, that is why another magnet deflected. One magnet will be deflected by another magnetic field. So here the deflection they observed, with respect to that Oersted confirmed that current carrying conductor producing magnetic field. Now converse, with the magnetic field can we produce the current? So those details I will give you. So let's go to the topic, that is electromagnetic induction. So before going to discuss about the production of current using magnetic field, so first let me give the details about electromagnetic induction as a definition. The phenomenon of generation of current or EMF. So here EMF means electromotive force that we can treat as voltage by changing the magnetic field is known as electromagnetic induction. So simply we are calling as EMI, nothing but electromagnetic induction. The EMF developed in the conductor by the process of EMF is known as induced EMF. Why? Because generally it is not there. By introducing the changing magnetic field, we are developing that one. So generally across the terminals of a particular conductor, that voltage is not there. We developed, we induced. So that is why that is induced EMF. By applying the magnetic field, we did. So that is why we are calling that as induced. So induced voltage developed due to that current will pass, that current flowing through the conductor, that we are calling as induced current. Next, magnetic flux. So before going to the experimental details, so let me give complete details about magnetic flux. Why? Because here the change of magnetic flux only produces the EMF or induced current. So for that, first you should have clear knowledge on magnetic flux. So magnetic flux means the total number of magnetic field lines of force passing through a closed surface are called magnetic flux. That if you analyze with respect to a symbol. So it is denoted by phi. So actually phi means maybe electric flux or magnetic flux. So in particularly if you mention B, that is directly it is magnetic flux. So in case of electric flux we are using phi E as a suffix. Unit Weber or Maxwell, another unit also there, that is Maxwell. The relation between them, 1 Weber equals to 10 to the power of 8 Maxwell. Now to get the mathematical analysis of the magnetic flux, to represent the magnetic flux with respect to magnetic field and the flux where it is connected to a particular area. So once observe the diagram. So particular area A we are observing with respect to the normal. Why I am saying with respect to the normal? If you change the your view, if it is not along the normal, then area decreases. So for that, just simple one experiment you can do. For example, you are observing the mobile display or laptop display now while watching the video. Now the change the elevation. So now you are in front of the display. Now if you change the view, if you are not observing along the normal, just if you see little bit, then the area will change. Or no need to change your face, just change the display plane little bit, means rotate the display little bit. So if it is the laptop, just change the screen little bit, then you can observe the area change. So either area may increases or decreases, that is according to view. So along the normal you can observe maximum area. If you change the view not along the normal, definitely there is a small decrease in area. If you convert the display, then area decreases and become 0 also. If you observe along the plane of the material, then so for example if your view is parallel to the display, you can't see the display, so the total display area will be 0. So along the normal it is maximum. So that is why normal view area capital A. Now for example, B is the magnetic flux, it's making an angle theta with respect to the normal. Now along the normal, the component of magnetic flux we can represent as B cos theta. So here theta we consider with respect to the normal. So B magnetic field in this direction, then along this direction it is the adjacent component. So that is why B cos theta. So according to magnetic induction definition, magnetic induction or flux density, nothing but magnetic flux per unit area. So that you can also write like this: flux phi B equals to B bar dot A bar. So here B bar magnetic field, it is a vector quantity that we already know. So here area also we are treating as a vector. Why? Because along the normal it is having one value. If you change the elevation, then value is decreasing. With respect to direction, the value is changing, means that is a vector. So here area we can treat as a vector. Why? Because the magnitude of the area changing with respect to the direction. So A bar is the area vector. Then the dot product of B bar and A bar, nothing but BA cos theta. Now B cos theta is the magnetic field according to the magnitude, and A is the area along the normal. Then the flux along the normal is phi B. So phi B flux along the normal to the plane in the diagram, that is AB cos theta. Now we can write like this simply: BA cos theta or B bar dot A bar. So just I am keeping B bar dot A bar. So I want to convert into integral form. So in integral form, phi B equals to B bar dot A bar. Here A is the total area. Now the total area, for example, you divided into small areas, dA areas. Now sum of all areas gives the total area. The sum of all areas means integration of dA small area, you will get the total area. So B bar dot into integral dA bar is the total area. Here integral dA bar is the total area. So A bar we can represent like this. Now that B bar also we can write inside, then it will be flux phi B equals to integral B bar dot dA bar. So it is almost like Gauss law in magnetic field. So Gauss law in electric field, that is phi E equals to integral E bar dot ds bar. So similarly here magnetic flux equals to integral B bar dot dA bar. Further, the magnetic flux dimensional formula. So if you study dimensional formula also, according to the formula B bar dot A bar, so that B bar dot A bar we can convert in such a way that to know the magnetic flux, we are introducing the known physical quantities. So directly B we don't know, but we are assuming one thing. So accordingly we can introduce the known physical quantities, which dimensional formula we know clearly. So then we can write the dimensional formula for magnetic flux. So directly B dimensional formula if you don't know, then we can convert into one simple known formula, so in which all physical quantities dimensions if you know, then it is easy for us. So here we know that F is the force on a charged particle Q moving perpendicular to the magnetic field B with velocity V is F equals to BQV. Actually it's BQV sin theta. For example, if it is perpendicular, that I mentioned already, so we know the formula F equals to BQV. So in this B equals to F by QV. So now instead of B we can substitute F by QV. So we want only dimension, so that is why just dot product is not matter, we want just only dimension. So for that we want only quantities magnitudes. So instead of B, F by QB into area A. Now further, F dimensional formula we know in class 11 many times we used dimensional formula of force MLT power minus 2. A area means that is length into breadth, so L into L square, and Q dimensional formula directly it is not there, so again we have to convert. For that, current nothing but rate of flow of charge, or simply Q by T time is nothing but current, so we have to convert the charge into current into time. So current equals to charge by time, so charge equals to current into time. So if you substitute now all physical quantities dimensions we know, so F and A already I mentioned, so I current direct dimension, and T time dimension capital T, and V velocity nothing but LT power minus 1. If you substitute all, so as it is flux formula F by ITV into A. So now if you substitute dimensions, so F dimensional formula MLT power minus 2, and area dimension L square, and I current small I dimension symbol capital I, or in some books they are using A also capital A. So capital A is giving confusion, why? Because already area A is there, so that is why I'm using capital I is the dimension symbol for current, and T time dimension symbol capital T, and velocity LT power minus 2. So here clearly we can get cancel T and T power minus 1, and as well as L and L. So then the remaining all if you mention M L square and T power minus 2, and in denominator I is there, if you shift to the numerator then I power minus 1, M L square T power minus 2 into I power minus 1. This is the dimensional formula for magnetic flux. Next, experiments of Faraday and Henry. So here both did few experiments, and from that they are mentioning few points. The first experiment, that is current induced by a magnet. So for that once observe the diagram. So here one closed coil is there. So that closed coil is connected to the galvanometer to know the current, either it is there or not, it connected. And if you pass the magnet towards the coil, so here you can observe arrow mark, so the magnet is coming towards the coil, and here north pole facing the coil. So if it is coming towards, then there is a current, and direction we will discuss in the next class. So here just only I'm mentioning the current. So here the change of magnetic flux, here I'm using the word change of magnetic flux. Reason, if the magnet is a little bit away from the coil, then number of lines of force are very less. As it is coming close to the coil, then number of lines of force increases. So here you can see area, and here you can see the area. Same area if you consider here more number of lines of force, here less number of lines of force. Reason, the magnet here it is at long distance, here it is at nearby. So as flux coming towards, or magnet coming towards the coil, then magnetic lines of force will increase. So due to the increase in magnetic flux, or due to decrease in magnetic flux also, so that is why simply we are using the word due to change in magnetic flux linked with the closed coil, there is a EMF, there is a induced current in the coil. So that is observed by the Faraday. So this is the first experiment. So here coil is at rest, magnet is moving. For suppose if you do in reverse, then also induced EMF will develop in the closed coil. So either magnet moving towards the stationary closed coil, or closed coil going towards the stationary magnetic field or stationary bar magnet, the effect will be the same. There will be a change in magnetic flux, so which induces the induced current or induced EMF. Now the second experiment, current induced by a current. So for that, once observe the diagram. So in the diagram, for example, one coil is at rest and it is connected to the galvanometer. Then if you move another coil, so which is connected to a battery, so in that there is a current. So the current carrying coil produces magnetic field, that we already learned according to Biot-Savart's law. The magnetic induction value produced at the center at a particular point also we derived. So here current carrying coil also it is like a bar magnet. So the current carrying coil coming towards the coil, so definitely there is a change in flux, there is an increase in flux. As it is moving away, then also there is a change in magnetic flux. So the change in magnetic flux produces induced EMF here. So with respect to that, we can observe the deflection in the galvanometer. That means there is a current induced due to change in magnetic flux. That is the current in the coil producing magnetic field, and we are moving the coil towards, so there is a change in magnetic flux linked with this closed coil C1. So induced current, induced EMF is there. So this is the second experiment. So current induced by a current. Next, third experiment, current induced by changing current. So here first experiment, the magnet is coming towards a coil. In second experiment, a current carrying coil coming towards the coil. Now in last case, there is no movement in the coil. So both the coils are at rest, but even then, due to the change in current in one coil induces magnetic field in the another coil. For example, in C2 coil, we connected an AC supply. That AC supply is nothing but AC, alternating current. Continuously it is altering, means there is a change in current continuously. So due to change in current, definitely there is a variable magnetic field. So that variable magnetic field means increasing, decreasing magnetic field connected to the closed coil induces the EMF in the first coil C1. So here both are relatively at rest, but even then due to the change in current produces change in magnetic field, means change in magnetic flux, which induces the induced EMF in the coil C1. So in this case also we can observe the deflection in the galvanometer. So it's the third experiment. Next, Faraday's laws of electromagnetic induction. So from all these, he is giving two laws. The first one, Faraday's first law, whenever the amount of magnetic flux linked with a closed circuit changes, an EMF is induced in it. So according to that wording, so if magnetic flux linked with the coil changes, there is a EMF. So that magnitude of EMF that is there in the second law, that is the magnitude of induced EMF in the circuit is equals to the negative rate of change of magnetic flux through the coil. So here just magnitude wise I wrote equal, but in particularly it is opposite effect. change of magnetic flux, the coil is opposing. So that is why we will represent with the negative sign. So that is why the induced EMF proportional to rate of change of magnetic flux, but I'm using the word the negative rate of change of magnetic flux actually. So here magnitude wise both are proportional. If you change more magnetic flux, there will be a more induced EMF but in opposite direction. That opposite direction and all details with respect to Lenz law we can study. That is the next topic that I will explain in the next video. So here according to Faraday second law, the induced EMF is proportional to change in magnetic flux, or we can write equal. So there is no proportionality constant, so directly it is equals to minus d phi b by dt, means the proportionality constant value 1. So here rate of change of magnetic flux we can also represent. So it is a change. So for example, final flux, initial flux phi2 minus phi1, and dt change in time t2 minus t1. So we can represent like this also. Now if the closed coil having n number of turns, due to one turn we are getting this effect. If due to 2 turns, then it will be doubled. If there are 3 turns, it will be 3 times. So due to n number of times, the effect will be n times. So induced EMF E equals to minus n into d phi b by dt. So here induced EMF produced in the coil which is having n number of turns is equals to minus n into d phi b by dt. Induced current. So according to Ohm's law, V equals to IR. So just now we analyzed the EMF. EMF nothing but voltage. So according to Ohm's law, V equals to IR, that we can write I equals to voltage by time. Sorry, voltage by resistance. So induced current flowing in the coil according to Ohm's law, current equals to voltage by resistance, nothing but E by R. Now EMF according to Michael Faraday, for a coil of n number of turns, minus n into d phi b by dt, so by R. So this is the induced current in a coil of n number of turns. Now from this we can get the charge also. So electric charge flows due to induced current. So here current nothing but charge by time. So charge equals to current into time. So here already current is there. So here if you shift the time towards left side, then I into dt, nothing but charge. So we can get charge q equals to I into dt. So if you shift dt, then remaining minus n by r into d phi b, that is only change in magnetic flux. So this is the induced current expression.
Namaste students, welcome to physics class. According to Michael Faraday, change in magnetic flux produces current in closed conductor. Now the current produces means definitely there will be a current in a particular direction. What is the direction of current? If north pole of the magnet going towards the closed coil, then magnetic field produces the current in which direction? That we are going to learn in this video.
Before going to explain the Lenz law details, let me give the recap about Faraday's laws of electromagnetic induction. Faraday's first law. So according to Faraday's first law, whenever the amount of magnetic flux linked with a closed circuit changes, an EMF is induced in it. So compulsory, the magnetic flux should change which is connected to the closed coil, then in the coil there will be a induced EMF. The magnitude of induced EMF is explained through his second law, that is Faraday's second law. So according to his second law, the magnitude of induced EMF in a circuit is equal to the rate of change of magnetic flux through the circuit. So here the magnitude of induced EMF, how much will generate, that depends upon the rate of change of magnetic flux linked with the closed circuit. So here the negative rate of change of magnetic flux exactly equals to EMF, but in general they will say the change in flux induces EMF. So that is why here we are mentioning induced EMF is nothing but rate of change of magnetic flux, means induced EMF proportional to rate of change of magnetic flux, but in deep if you study that both are opposite, so that is why we will indicate negative sign. That is, induced EMF equals to minus negative rate of change of magnetic flux. d phi b by dt means with respect to time there is a change in flux. The negative rate of change of magnetic flux is equals to the EMF induced in the closed circuit. For suppose if there are n number of turns, so before that here the rate of change of flux we can also indicate d phi b means a change in flux, that is final flux minus initial flux phi 2 minus phi 1, and as well as time, initial time t1 and final time t2 while changing. So two instant of times if you study the flux and time, then phi 2 minus phi 1 by t2 minus t1 is the rate of change of flux, which is equals to EMF. So for n number of turns the EMF also n times. If the closed coil contains n number of turns, then EMF induced will be E equals to minus n into d phi b by dt. Lenz law. It gives the direction of EMF induced in the closed coil. So according to Michael Faraday, if there is any change in magnetic flux linked with the closed coil, there is a induced EMF, there is a induced current in it. So current passing in the closed coil means definitely there will be a direction. So what is the direction according to the change of magnetic flux? That is explained by Lenz law. First definition. So according to definition, the direction of the induced current is such that it opposes the original change producing it. So here looking like a small confusion, read carefully. So induced EMF will generate in such a way that it should opposes the original cause. So let me explain through a diagram. So for example, here there is a closed coil. For this closed coil, one bar magnet continuously giving the change of magnetic flux. For suppose the north pole is approaching towards the closed coil, means continuously there is a increase in magnetic flux. Now according to Lenz law, what he is saying here, induced current will generate in the closed coil in such a way that it has to opposes the change. So here flux change is there, it has to oppose. So here north pole coming, so it has to oppose this one, means compulsory it has to generate the north pole here. So to generate the north pole here, compulsory it has to produce the current. So the current will generate in this direction, so as shown in the diagram. So if induced current develops here in this direction, then just apply Ampere's thumb rule. So here you can see the thumb direction, that is current direction. Then magnetic flux will generate along the curling of fingers, means the curling of fingers indicates the north pole. So here it will generate the north pole, then other side south pole. So induced current will generate in the closed coil, and that induced current produces the magnetic flux. That magnetic flux will try to opposes the bar magnet to stop the change of magnetic flux. So here the closed coil doesn't like to allow the external magnetic lines of force through it. So that is why it is generating. Next, same thing I want to explain by giving one more example with one more diagram. So here clearly you can see the flux going inside. So here V is the velocity and bar magnet, north pole, south pole. So here north pole approaching the closed ring. Then whenever the flux changing, then it has to generate the induced current. So here you can see the arrow mark. Induced current will develop in it in such a way that it will behaves like a magnet, means it behave like another bar magnet to stop the moving bar magnet, that you can see clearly here. So induced current will develop in the coil. That induced current will create the magnetic flux and it will try to stop. I hope you understand. Now, applications. For suppose the bar magnet is moving away, then what will happen? So if the bar magnet is going away, that means the flux initially when bar magnet very near to the coil, more magnetic flux will be there. As it is going away from the closed coil, there is a decrease in flux. So now this closed ring don't like to change. So here try to observe the major concept. Here the closed coil don't like to change anything. So here flux increasing initially, it don't like to increase. Now here magnetic flux decreasing, it don't like to allow decreasing also. So it doesn't like to change the magnetic flux linked with this coil. So now north pole going away, magnetic flux decreasing, so it has to develop the magnetic flux in opposite direction. So current will generate, induced current will generate in this direction, then the flux will develop in this direction. So here flux decreasing, so it has to generate the flux in the same direction. So it will create the magnetic field around it like this. So north pole is going away, so you don't like to allow the north pole to move away, so it will create the south pole. By south pole it will try to drag the bar magnet, so it will generate the EMF or induced current according to the opposition, means according to the change of flux it will create. So induced current will develop which opposes the change. One more example. So here coil. So for just I mentioned one ring or just one turn. Now for example n number of turns are there, even then the concept is the same. For suppose the bar magnet is approaching towards a coil, then this coil don't like to increase the or don't like to allow the external magnetic lines of force to it, so it will generate the magnetic field to opposes the external magnetic field. So for that it has to generate the current, so inside induced current will develop and finally it will try to stop the external magnetic flux. So for that it has to generate the flux in which direction? So according to ampere, so here we should get north pole. So for that just observe the arrow mark. So thumb, if you keep in that direction, the curling of fingers will come outward, so north pole will come, and that induced current produces the north pole and try to stop this north pole coming close to the coil. That means current generating in this direction. That means according to this bar magnet, the current direction is in anti-clockwise. So anti-clockwise direction. So for that here it will be positive and this side it will be negative. So you can observe clearly in the diagram. For example, if the bar magnet is moving away, then if it is moving away, so then also this coil don't like to go away. So it will try to stop this bar magnet. For that it has to generate the south pole here. To generate the south pole, here it has to generate the north pole. Means current has to pass in this direction in such a way that north pole will create here and south pole will be here, so that south pole will try to stop the bar magnet. So the change of magnetic flux induces the current, but according to Lenz law, this is saying in opposite. So there is a change to oppose that one. Here inside the coil in opposite direction something will develop, that is induced EMF or induced current. So here it is in opposite direction. So according to bar magnet it will be in clockwise. So in clockwise induced current will develop. Special cases. For suppose both are moving, both are in the sense bar magnet, coil, both are moving. For suppose v1 velocity of bar magnet, v2 velocity of the coil. For suppose bar magnet moving with more velocity and coil velocity is less, then for example, before going to that, if both are moving with the same velocity, then there is no change in magnetic flux, then there is no EMF. So compulsory the flux has to change. If both are moving with the same velocity, then induced current will be 0. Okay. Now if velocity is more for bar magnet, then continuously the bar magnet approaching the coil. So according to the case, so flux will increase. So this coil has to opposes the change of flux. So that is why it will generate the north pole and it will try to stop that one. So that is why induced current will develop in this direction. So according to bar magnet, it will be in anti-clockwise direction. It will try to stop the increase in magnetic flux by the bar magnet. Now one more case, that is reverse case. For suppose coil is moving with more velocity and bar magnet is moving a little bit slow. In that case, so here coil is going away means continuously there is a decrease in the magnetic flux. So here coil don't like to decrease the flux, so it will generate to compensate the decreasing flux. So for that it has to generate the current in clockwise direction to compensate the decrease in flux, means it don't like to decrease, so it will generate the south pole here to stop the or to attract the bar magnet to compensate the loss or compensate the change. So that is why north pole, south pole and in clockwise direction current will generate. Now if both are moving, in that case also same, if both are approaching each other. So in that case also it is same, if both are coming close to each other, there is a change in flux, so there is an increasing flux. So here north pole coming towards, so north pole will generate. For suppose here if you keep south pole, then here it will generate south pole. Here flux continuously increasing, it has to oppose, so for that it will generate accordingly. So north pole coming, so that's why anti-clockwise, if you keep here south pole, then in clockwise direction current will generate with respect to the bar magnet and it will try to stop the change of external magnetic field. So according to Lenz law, the closed coil don't like to allow external magnetic lines of force, it don't like to change, it opposes in such a way that it has to stop the original cause, it has to opposes the original cause. Now if both are moving away, so then also same. So here the coil don't like to change the magnetic flux, here magnetic flux decreasing, so here it will generate the south pole to stop the change. So that's why here it will create the south pole. So to create south pole, here it should be north pole. So for north pole current has to pass in this direction, then only here it will be north and here it will be south. Now Lenz law is indirectly giving conservation of energy. So with simple diagrams I will show that one. For example, a bar magnet north pole approaching a closed coil. Then the closed coil will generate the north pole, means it will try to give the north pole facing to the bar magnet north pole. For example, if the bar magnet is moving away, then you don't like to decrease the magnetic flux, decreasing in the magnetic flux, so it will generate the south pole and it will try to stop the north pole to move away. Okay, so whenever there is a continuous change in magnetic flux, there is induced EMF. As long as the flux changing, there is a EMF. Whenever you stop the bar magnet, then induced EMF will be 0. If it is not the case, everybody will purchase one big magnet, they will keep near the coil and the coil will give the current, that current we will use for household purpose. So it is not like that. So as long as we are giving the kinetic energy to this one, that kinetic energy is converting into electrical energy. So here conservation of energy going on, nothing is creating here. That is Lenz law. So Lenz law explaining the conservation of energy. For example, in the diagram you can observe north pole, south pole. So magnetic field along this direction, that you can see north pole to south pole magnetic field direction. So here forefinger indicating the magnetic field direction and thumb indicating the direction of the conductor. So here you can see a conductor. So that conductor, for suppose moving upward, for suppose direction of force, or for example it is moving upward. So inside a magnetic field, a conductor moving perpendicularly. So that conductor is perpendicular to the magnetic field and moving perpendicular to the magnetic field. Okay, so here three directions are there. So magnetic field direction, other than that two more directions are there, two perpendiculars. Okay, so in one direction, for example, if conductor is moving, so here conductor, motion and magnetic field both should be perpendicular to each other. Then for these two, one more direction will be their perpendicular direction. Along the direction, induced current will develop. That is indicated by right hand middle finger. So once again, so here magnetic field direction indicated by forefinger and motion of the conductor indicated by the thumb. Then inside the conductor, induced current will develop in such a way that current will pass from this direction to this direction, means in the direction of middle finger of the right hand. Means here positive charge will develop. So here you can see positive charge and here negative charge will develop. Then current will pass from positive to negative. Means indirectly you can say that electrons are moving from here to here. Means in this direction to this direction. Okay. I hope you understand. The EMF induced. That is, the magnitude of induced EMF in a circuit is equal to the negative rate of change of magnetic flux linked through the circuit. So here I used negative rate of change. That means actually if you consider EMF as positive, that affect the change opposing properties EMF. EMF induced in such a way that it try to opposes the change in magnetic flux. So that is why it is on opposite sign. So if EMF is positive, the change of flux is negative. So that is why we can write like this: induced EMF proportional to the rate of change of magnetic flux, but in opposite direction. Negative sign indicates opposite direction. So here, how much change created in a closed circuit, that much induced EMF will develop. If change of flux is more, EMF induced will be more. That magnetic expression EMF E equals to minus d phi v by dt. So induced EMF is equals to negative rate of change of magnetic flux. So here the rate of change of magnetic flux we can also represent like this. For example, initial flux phi1 and the final flux phi2. So the change of flux is phi2 minus phi1, and as well as time. So initially t1 time, so it changed to t2 time. So then the time interval is t2 minus t1. Now, if the closed coil contains n number of turns, then, so this is due to one coil of one turn. If there are two turns, then EMF will be doubled. If there are three turns, then three times. If there are four turns, then four times. If there are n turns, that is n times. So EMF we can make it more by arranging more number of turns to the coil. So induced EMF induced in a closed coil of n number of turns, that is E equals to minus n into d phi b by dt. Motional electromotive force. So to analyze this one, just consider one diagram. So before going to analyze the diagram, so what is the topic actually that is there clearly in the heading, motional. If something is moving, then electromotive force will develop. That means if a conductor moving in magnetic field, definitely there is a electromotive force in the conductor. So for that purpose, consider A, B, C, D, an area where uniform magnetic field B is there. Now, in the uniform magnetic field, for suppose PQRS one rectangular conductor. So it's just a conductor. Okay. So that is there in magnetic field as shown in the figure. Now, for suppose if we are moving this one towards left side as shown in the diagram, slowly with uniform velocity v, and qr is for suppose length of the conductor, then as we are moving this one in this area continuously, there is a change in magnetic flux. So if you take it out, continuously flux decreases. If you are keeping inside, then flux will increase continuously. So here it is going out, so flux decreasing continuously. So just to keep it in mind, at last we will analyze current direction by using the change in magnetic flux. So first let me give the theoretical analysis, afterwards current direction we will see. For suppose the area of the coil inside the magnetic field at a particular time. So for suppose at a particular time, y is the length as shown in the diagram, and L already we mentioned for QR, then the total area inside the magnetic field, that is dA, equals to L into Y. So coil area inside the magnetic field at a particular time, L into Y. Now the magnetic flux easily we can mention now. So magnetic flux linked with the coil at any time. So B magnetic field we know and area we know, then magnetic flux equals to magnetic field into area. So magnetic field B into area L into Y. So therefore we can give the EMF details now. For that purpose, the rate of change of magnetic flux linked with the coil, if you analyze, that is d phi v by dt. If you differentiate with respect to time, then b l y with respect to time differentiation gives rate of change of magnetic flux. So further here b constant, l constant, as we are moving y will change. So we can write this expression like this: d phi v by dt equals to b l into dy by dt. So here rate of change of y, nothing but rate of change of displacement, nothing but velocity. So instead of dy by dt, we can write velocity expression. So therefore rate of change of flux equals to b into l into v. If E is the EMF for suppose, then according to Faraday's law, induced EMF equals to negative rate of change of magnetic flux, E equals to minus d phi b by dt. So instead of d phi by dt, we can write BLV. If you substitute BLV, then motional EMF E equals to minus B into L into V. So if a conductor moving in magnetic field, there is a EMF across the terminals of the conductor that depends upon magnetic field. If magnetic field strength is more, then more EMF will generate across the terminals of the conductor, and if length is more, then also EMF will be more, and as well as if it is moving quickly, then more EMF will generate, because more change of flux will happen if we move quicker. If we move slowly, then change of magnetic flux will be very less. So motional EMF depends upon three factors. So this induced electromotive force EMF BLV is called as motional EMF. Now the diagram if you analyze now. So as the conductor moving perpendicularly in magnetic field, so then there is a EMF across these terminals. So due to that, current will pass. So induced EMF generating, with respect to that current will pass. The current direction we can analyze with respect to the change of flux. For example, here the coil doesn't want to change the magnetic flux. As we are moving this one right side, flux decreasing continuously. So the coil don't like to change the flux in the area. So that is why it will generate the flux in the same direction and it will try to keep the value same. So for that purpose, so here into symbol means magnetic field perpendicularly inward. So according to the diagram or according to the display, the magnetic field perpendicularly inward. So in inward direction, magnetic flux decreasing. So inside the coil, EMF will generate in such a way that flux should generate or magnetic field should generate in the same direction. So for that, according to Ampere's right hand thumb rule, so current should pass, means current should induce actually in clockwise direction, so that magnetic field will generate inward, so that it will try to stop the change of magnetic flux. So that is why magnetic field generate in clockwise direction. The same current direction we can analyze with respect to Fleming's right hand rule also. So according to Fleming's right hand rule, if right hand thumb, we have to keep our right hand three fingers, first three fingers perpendicular to each other. Then if thumb indicates the direction of motion of the conductor and forefinger if it indicates the magnetic field direction, then middle finger indicates the induced current direction. So now if you try, according to the display, magnetic field inward to the display, so keep your right hand pointing finger inward to the display and show the thumb towards the velocity direction. Then your right hand middle finger will show upward direction. That means towards R to Q. So that is the current direction. So with respect to Fleming's right hand rule also, induced current direction we can analyze. So in any way we can get the current direction, that is in clockwise direction. Next one problem. A wire of length 0.3 meter moves with a speed of 20 meter per second perpendicular to the magnetic field of induction 1 Weber per meter square or Tesla. Calculate the induced EMF. So they're asking to find the induced EMF E. So that is wire is moving. So motional EMF, that is E. So just now we analyzed the formula is BLV, simple formula. So given that if you write velocity V equals to 20 meter per second and length 0.3 meter and angle so 90 degrees. So actually that effect is not there here. So magnetic field B equals to 1 Weber per meter square. So generally we will analyze the topic with respect to angle 90 degrees only. So induced EMF E equals to BLV. So if you substitute all, E value 1 and velocity 20 and length 0.3. So if you multiply all, you will get the answer 6 volts. One application. Find the induced EMF of a rod of length L rotating with angular velocity omega in a uniform magnetic field B as shown in figure. The diagram. So here magnetic field perpendicularly outward. So dot indicates, for example, perpendicularly outward, and a length L rod moving in uniform magnetic field B with angular velocity omega. Then we have to find out the induced EMF. So here they mentioned omega, asking about induced EMF. So here for that angular velocity of the rod, they mentioned omega, that we can analyze as 2 pi by t. So here capital T is nothing but time period of the rod. So it is moving with uniform velocity. So time taken to finish one rotation, that is time period. Now for induced EMF, we have to find out the rate of change of flux. So the change in flux in one rotation. So if it completes one rotation, then how much flux will change? So here magnetic field into the entire area covered in one rotation, that is magnetic flux change. So magnetic flux nothing but B into A. So magnetic field into area. So magnetic field B, but area covered with the L radius. So here this point is fixed, it is rotating with angular velocity omega, so it will cover the area pi L square. So the total area covered is pi L square. So in one complete rotation, so the change in flux in one rotation we can analyze as B into pi L square. Now, according to Faraday's law of electromagnetic induction, the magnitude of induced EMF E is nothing but rate of change of flux. So just only according to magnitude. Here negative sign I am not taking. We want only magnitude. So for that purpose, so only d phi by dt. So the change of flux, that is B into pi L square by dt. So this is we analyzed for one complete rotation. So one complete rotation means time period capital T. So now the capital T they did not give in the given question. They mentioned omega, but we know that omega nothing but 2 pi by T. So instead of T, we can write 2 pi by omega. So if you substitute instead of T, 2 pi by omega, further pi get cancelled. So just we have only pi cancel. Then omega will go upwards. Then 1 by 2 into B into omega will go up, omega into L square. So this is the induced EMF generated across the terminals of the rotating rod in uniform magnetic field with angular velocity omega, that is equals to half B omega L square. Next, based on the given or derived formula, one problem, a wheel with 10 metallic spokes, each 0.5 meter long, is rotated with a speed of 120 revolutions per minute. It is not rotations, so these are revolutions, not per second, per minute. So be careful if they mention the units like this. In a plane normal to the horizontal component of the earth magnetic field He at a place, if He equals to 0.4 Gauss at the place, what is the induced EMF between the axle and the rim of the wheel? Take 1 Gauss equals to 10 to the power of minus 4 Tesla. This already we know. So first, if you analyze the given data, so the given data, angular velocity omega, so 120 revolutions per minute. So one revolution means it will cover total 360 degrees. So 360 degrees means 2 pi radian. So we have to convert into radian for SI system of units, and as well as denominator. So this is per minute. So 1 minute nothing but 60 seconds. So if you multiply with 2 pi by 60, revolution per minute will be converted into radian per second. So if 60 and 120 but get cancelled by 2 times, then 2 into 2 pi nothing but 4 pi radian per second. Next, length L they mentioned 0.5 meter. Next, magnetic field, horizontal component of earth magnetic field 0.4 Gauss or 0.4 into 10 to the power of minus 4 Tesla. Formula omega L and so if you substitute in the given formula half as usual instead of B 0.4 into 10 to the power of minus 4 and omega 4 pi and length as 0.5 whole square. So now further half as usual. So this one I am writing 4 into 10 to the power of minus 5 and 4 pi into 0.5 nothing but 1 by 2. So 1 by 2 whole square nothing but 1 by 4. Then 4 4 get cancelled and 2 divides 4 by 2 2 times, so it will be 2 pi into 10 to the power of minus 5. So 2 pi nothing but 6.28. So 6.28 into 10 to the power of minus 5 EMF, so unit volt. So this is the voltage across the rim and the center point. Motional electromotive force. So to analyze this one, just consider one diagram. So before going to analyze the diagram, so what is the topic actually? That is there clearly in the heading. Motional. If something is moving, then electromotive force will develop. That means if a conductor moving in magnetic field, definitely there is a electromotive force in the conductor. So for that purpose, consider A, B, C, D, an area where uniform magnetic field B is there. Now, in the uniform magnetic field, for suppose PQRS one rectangular conductor. So it's just a conductor. Okay. So that is there in magnetic field as shown in the figure. Now, for suppose if we are moving this one towards left side as shown in the diagram, slowly with uniform velocity v, and qr is for suppose length of the conductor, then as we are moving this one in this area continuously, there is a change in magnetic flux. So if you take it out, continuously flux decreases. If you are keeping inside, then flux will increase continuously. So here it is going out, so flux decreasing continuously. So just to keep it in mind, at last we will analyze current direction by using the change in magnetic flux. So first let me give the theoretical analysis, afterwards current direction we will see. For suppose the area of the coil inside the magnetic field at a particular time. So for suppose at a particular time, y is the length as shown in the diagram, and L already we mentioned for QR. Then the total area inside the magnetic field, that is dA, equals to L into Y. So coil area inside the magnetic field at a particular time, L into Y. Now the magnetic flux easily we can mention now. So magnetic flux linked with the coil at any time. So B magnetic field we know and area we know. Then magnetic flux equals to magnetic field into area. So magnetic field B into area L into Y. So therefore we can give the EMF details now. For that purpose, the rate of change of magnetic flux linked with the coil, if you analyze, that is d phi v by dt. If you differentiate with respect to time, then b l y with respect to time differentiation gives rate of change of magnetic flux. So further here b constant, l constant, as we are moving y will change. So we can write this expression like this: d phi v by dt equals to b l into dy by dt. So here rate of change of y nothing but rate of change of displacement, nothing but velocity. So instead of dy by dt we can write velocity expression. So therefore rate of change of flux equals to b into l into v. If E is the EMF for suppose, then according to Faraday's law, induced EMF equals to negative rate of change of magnetic flux, E equals to minus d phi b by dt. So instead of d phi by dt, we can write BLV. If you substitute BLV, then motional EMF E equals to minus B into L into V. So if a conductor moving in magnetic field, there is a EMF across the terminals of the conductor that depends upon magnetic field. If magnetic field strength is more, then more EMF will generate across the terminals of the conductor, and if length is more, then also EMF will be more, and as well as if it is moving quickly, then more EMF will generate because more change of flux will happen if we move quicker. If you move slowly, then change of magnetic flux will be very less. So motional EMF depends upon three factors. So this induced electromotive force EMF BLV is called as motional EMF. Now the diagram, if you analyze now, so as the conductor moving perpendicularly in magnetic field, so then there is a EMF across these terminals. So due to that, current will pass. So induced EMF generating, with respect to that, current will pass. The current direction we can analyze with respect to the change of flux. For example, here the coil doesn't want to change the magnetic flux. As we are moving this one right side, flux decreasing continuously. So the coil don't like to change the flux in the area. So that is why it will generate the flux in the same direction and it will try to keep the value same. So for that purpose, so here into symbol means magnetic field perpendicularly inward. So according to the diagram or according to the display, the magnetic field perpendicularly inward. So in inward direction, magnetic flux decreasing. So inside the coil, EMF will generate in such a way that flux should generate or magnetic field should generate in the same direction. So for that, according to Ampere's right hand thumb rule, so current should pass, means current should induce actually in clockwise direction, so that magnetic field will generate inward, so that it will try to stop the change of magnetic flux. So that is why magnetic field generate in clockwise direction. The same current direction we can analyze with respect to Fleming's right hand rule also. So according to Fleming's right hand rule, if right hand thumb, we have to keep our right hand first three fingers perpendicular to each other. Then if thumb indicates the direction of motion of the conductor and forefinger if it indicates the magnetic field direction, then middle finger indicates the induced current direction. So now if you try, according to the display, magnetic field inward to the display, so keep your right hand pointing finger inward to the display and show the thumb towards the velocity direction. Then your right hand middle finger will show upward direction. That means towards R to Q. So that is the current direction. So with respect to Fleming's right hand rule also, induced current direction we can analyze. So in any way we can get the current direction that is in clockwise direction. Next, quantitative study of EMF or analysis of physical quantities in electromagnetic induction topic. So far, we discussed about induced EMF and as well as induced current. So remaining physical quantities also I will introduce here. For suppose here PQRS is one iron rod arranged according to the diagram. So on this U-shaped alignment, for suppose PQ, one rod is there, for suppose that is moving with a velocity V as shown in the diagram. For suppose here I consider SR length is L. Now for suppose whenever it is moving, here there is a decrease in flux. So the change of flux produces EMF. So due to the EMF, current will generate in the circuit. So current will pass through PQ rod. So that current is called induced current. So the current I in the loop is I equals to E by R. So here induced EMF will develop. So that induced EMF by resistance is nothing but induced current. So here I is the current passing. So that we can analyze according to motional EMF, that induced EMF due to the velocity, that is BLV, that we already studied. If you substitute here, then induced current I equals to BLV by R. So here the current produced, the magnitude depends upon velocity of the conductor as well as length of the conductor and strength of the magnetic field, and as well as inversely proportional to resistance. It's a common property for resistance and current inversely proportional. Due to the presence of magnetic field, the force on PQ is, so here whenever the PQ started moving, induced voltage will develop, due to that induced current will generate, so it is the current carrying conductor now. So that current carrying conductor moving in magnetic field perpendicularly, so there is a force, that is Bill, actually Bill sin theta, so it is moving perpendicularly, so F equals to BIL, B magnetic induction into I into length of the conductor. So Bill or ILB, so F equals to, so now instead of induced current I, if you substitute BLV by R, so then BLV by R into L into B. So now if you multiply B into B square, L into L square into V by R, so B square L square V by R. Therefore, F equals to B square L square V by R. Now, the power required to push the rod with a constant velocity is, here we are moving the rod, so for that compulsory we have to do work. So to maintain a constant velocity, so compulsory we have to do some work, so there is a power. So that power P equals to, you can write as the force into velocity. So force expression already we derived, so that if you substitute here, so then power P equals to B square L square V by R into V, so V into V square, so that is the resultant formula, B square L square V square by R. So this is the expression for power generated due to motional EMF. Now, induced quantities and their formulae. So here I arranged name of the physical quantity and formula, and it is applicable for open circuit or closed circuit, and it depends on resistance and as well as SI unit. Let us see first one, induced EMF. So induced EMF according to Michael Faraday, E equals to negative rate of change of magnetic flux. So nothing but minus d phi by dt. So it is applicable for open circuit as well as closed circuit. And according to the formula, you can see here resistance expression not there. So induced EMF is independent of resistance. So if a conductor is moving or a closed coil is there, so what it may be the resistance of the coil, that induced EMF is same for all type of materials and resistance. So it will not depends upon resistance of the conductor. So unit is volt. So here induced EMF is nothing but voltage. Next, second one, induced current. So here induced EMF we know, so then with respect to that, by applying Ohm's law, easily we can get voltage is nothing but current into resistance, so current equals to voltage by resistance. So voltage d phi by dt by R resistance. So here induced current, so current flow compulsory it should be a closed circuit, and it depends upon, clearly it depends upon resistance, inversely proportional to resistance. Induced current inversely proportional to resistance, and it is induced current means a current, so unit ampere. Next physical quantity, charge due to induced current. So according to current definition, current nothing but rate of change of charge. So nothing but I equals to dq by dt. So dq equals to I into dt. So here if you shift dt towards left side, then you will get I into dt. So I into dt is nothing but d phi by r. So d phi by r nothing but dq. So here negative sign will not give any meanings, but here induced EMF and flux change both are opposite. Here negative sign has the meaning, but here quantity wise both are same. And current flow, rate of flow of charge, so that is possible in closed circuit, so that is why it is applicable for closed circuit. And according to the formula it is clear, it depends upon resistance and charge unit coulomb. Next physical quantity, force, that is if a conductor is moving in magnetic field, definitely there is a force on the conductor. So due to motional EMF, force will act on the conductor, that F equals to B square L square V by R. So it is applicable for closed as well as open circuit, and it depends upon resistance, and force unit is Newton. Next, last one is power. So power P equals to B square L square V square by R. So it is also same applicable for open and closed circuit, and it depends upon resistance, and unit is watt. Next, induced quantities analysis with graph. For example, consider a situation according to the diagram. So here magnetic field is there. In the magnetic field, so there is a U-shaped conductor. On the U-shaped conductor, for example, PQ1 straight conductor is moving with a velocity v as shown in the diagram. So for example, initially that PQ is coincide with SR, for suppose, means that is at x equals to 0 position, and continuously it can go and it can cross x equals to b position, and it can go up to x equals to 2b position. For example, it started from x equals to 0, slowly it went up to x equals to b position, and again it went up to x equals to 2b position, and afterwards, for example, it returned to the initial position, means again it traveled back. So in all these cases, if the conductor is moving continuously towards right side from x equals to 0 to x equals to b, then here area is increasing. As area increasing, flux increasing. Okay, so there is a change in flux induces EMF. So let us see one by one graphically. If you observe, so initially whenever PQ is coincide with exactly SR, then area 0. So area 0 means flux 0. Okay, so here you can see outward. For example, the rod is going outward from the magnetic field, and the remaining part coming inward. Okay, so first we are discussing outward. So whenever it is coincide with SR position, then flux 0. As it is going towards right side, area increases. As area increases, then flux increases. So flux increasing, and it is moving with uniform velocity. So uniformly it is increasing up to position L. Whenever it reaches L, further, even though the rod is moving, crossing B2 and going towards 2B, so B2, TO2 to 2B, then there is no increase in magnetic flux. Why? Because so magnetic flux is there up to here. So as a rod crossing in magnetic field, means for example moving in magnetic field, then there is an increase in magnetic field. But if it crosses this position x equals to b, further there is no increase in flux. So that is why it will follow as it is straight line. L to M, there is no increase in magnetic flux. But in return journey, again M to L, there is no change in magnetic flux. But afterwards, whenever it is coming close to RS, slowly area covered decreases, and it will become 0. So gradually flux decreasing, and it is becoming 0. Now here from K to L, so here you can see K to L as rod moving, so there is an increase in flux. So EMF will be negative. Why? Because EMF equals to minus d phi by dt. So here flux positive, so EMF negative. Okay, now in return journey, flux decreasing. So decreasing in the sense means negative sense, so EMF positive. So that is why graphically we will get like this, and it is a motional EMF, that EMF value B into L into V. So magnetic field B for suppose, and L is the length of the conductor, and V is the velocity, then BLV is the motional EMF. Simply we can call as induced EMF. Now force. So as it is going outward, then the force, so here EMF negative, so force also negative, as it is that value is b square L square V by R that we derived in previous slide. Now here EMF is positive, then same quantity plus b square L square V by R is the force. But if you come to power, so power is a positive quantity, so that is why here from K to L power positive, and as well as in return journey also power positive. So that is why here EMF negative, so that is why force negative, but power is nothing but a positive quantity, so that is why same in both the case 0 to B or B to 0, so that is B square L square V square by R. So this is the graphical analysis for induced EMF or flux, EMF, force and power. It's a very important topic. Many times this topic asked in CBSE board exam. Next, conceptual questions. For suppose, what is the direction of induced current in metal ring 1 and 2 when current I in the wire is increasing steadily? The diagram, for example, so if you observe the diagram, so here two coils are there and current passing in the straight current carrying conductor, for example I is the current, and this current is increasing continuously. Then as it is increasing, current increasing means the magnetic field produced by the current carrying conductor also increasing continuously. So here in the coil there is a flux linked and that is changing. So as current changing, magnetic flux will change. Current increasing, magnetic flux increasing. So this coil don't like to increase the flux. So it will generate the induced current and it will try to stop the change in magnetic flux. So for that purpose, in coil 1, current has to generate in clockwise direction. So just analyze. If you keep your right hand thumb in the direction of current in straight wire, then curling of fingers will come here outward. Your right hand curling of fingers are coming outward. So in this coil, the external magnetic field should not pass. So for that purpose, this coil has to generate the flux inward. So here magnetic flux coming outward, so current will generate in this direction. Just keep your right hand thumb in this direction, then curling of fingers will show inward. Okay, so due to this straight current carrying conductor, flux coming outward, so this coil will generate opposite flux, inward flux. For that it will generate the current in clockwise. So at the same time, what about in coil 2? In the second coil, here flux going inward. So if you observe with respect to your right hand thumb, so right hand thumb rule, Ampere's law, so thumb indicating the current direction, then curling of fingers are going inward. So as flux going inward, this coil don't like to allow the external magnetic lines of force to increase and passing through the coil, so it will generate the flux outward. So to generate the flux outward, keep your right hand thumb again, then curling of fingers if you show outward, then current direction will be in anti-clockwise direction. So we can conclude that it will be clockwise in ring 1 and anti-clockwise in ring 2. One more question. In the given figure, mark the polarity of plate A and B of a capacitor when the magnet or magnets are quickly moved towards the coil. So this is the diagram. So just observe, both the magnets are coming towards. So here north pole coming towards, here south pole coming towards the coil, and the coil ends connected to capacitor plates A and B. So just imagine A and B are just out to the display, and this curved part is back side of the display, this is front side of the display, and this entire area facing, for example, north pole. Okay, like that diagram. Now as the north pole coming towards, compulsory this coil has to stop the increasing flux or crossing the flux through the coil. So for that it has to generate the current. With respect to that current, it has to generate the north pole here. So to generate north pole here, current has to pass. So curling of fingers should come towards left side. So for that current has to pass from A to B. Then only, so if current direction is A to B, then towards the B, if you keep your right hand thumb, then curling of fingers will show towards north pole, means north pole of the bar magnet. So to face North Pole here, compulsory curling of fingers of your right hand should show like this. So current will pass from A to B. So if current generated or current induced and it is passing from A to B means A should be positive and B should be negative. That means plate A will be positive plate while plate B will be negative plate. So current passing from A to B. So A is positive, B is negative. Before going to the topic, once observe the picture. So here in this picture, there is a water flow. You can observe water flow while taking the curve. So here fast flow and here little bit slow. Due to that, here you can observe small wrills. So whenever you are observing huge flow, velocity difference, then there is a whirl or some whirls will form in the river flow. So generally at the time of floods, we can see clearly the number of whirls. Same type of thing we can observe in electromagnetic induction concept also. So that is the topic, Ide currents. So Ide current, how they will generate? That is, a changing magnetic flux can induce a swirling current in a conductor. Means, if you can observe the diagram, so if a conductor is moving in magnetic field, then so due to the relative motion of conductor or any magnet, so compulsory there should be a relative motion. So due to that, there is a whirl in the conductor, means electrons will get sudden rotation. So that statement wise, if the conductor and magnetic field are in relative motion, the magnetic force on charged particles in the conductor causes circulating currents. This circulating current we are calling as Ide current. So here the Ide current directions also we can see. So whenever it is coming into the magnetic field, means flux is increasing, so it has to stop. So in that manner, here in anti-clockwise direction flux generated. Whenever it is going out of the magnetic field, so flux decreasing. So you don't like to change the decreasing flux, so that is why current will generate in clockwise direction. That you can analyze according to Lenz's law. So here induced current, Ide current is also like a induced current, so that opposes the original cause. So by applying Lenz's law, you can get the direction of electron rotation. Now about Ide currents. Ide current gives rise to magnetic fields that oppose any external change in the magnetic field. So the magnetic field change, these are opposing. So that cause is Ide currents. So that you can see in the diagram. So here one coil is there. That coil is connected to alternating current. So here alternating current means continuously the polarity of the voltage is changing. So alternating current is the next topic. There you will get a clear idea what is alternating current. But just consider, so alternating current means fixed voltage will not be there. Means in the sense polarity of the voltage not fixed. The magnitude of voltage is fixed average value, but polarity will change continuously. So that type of current if you give, so this is a current carrying coil produces magnetic flux. So due to the change of magnetic flux here inside the conductor, so the change of magnetic flux they don't like to attain, so that is why they will generate the wrills, means electrons will rotate, they will generate the Ide currents and they will try to stop the change in magnetic flux. So here magnetic flux hitting the conductor surface, so from the conductor magnetic field will generate, means Ide currents will develop and magnetic flux will generate in opposite direction to compensate the increase in flux or crossing the flux through the conductor. So this is the concept of heat current that you can see in the diagram also. So here for example, individually, for example, you cutted the conductor like this, and if you just move, so whenever you are just moving, then or it is coming out of the conductor here according to this position, so then you can see the wheels in clockwise direction. Here the clockwise direction reason magnetic flux is going inward for suppose, then it don't like to decrease the magnetic flux, so it is try to develop the magnetic flux in the same direction, means inward. So to develop the magnetic field inward, so apply Fleming's right hand grip rule. So curling the fingers you have to keep inward to this conductor, then your thumb indicates the direction of clockwise. So that is why here it a current in clockwise direction. Now applications of ED currents. Many applications are there. So one by one, it is used to control the vibration of the string or vibration of the needle in galvanometer, voltmeter, ammeter. So that is simply by concept of electromagnetic damping we are using. So ED current concept is useful. I will explain in the next slide clearly with diagram. Next one, induction furnace. Next, electric power meter, and one more, magnetic braking in electronic trains. So many are there. So mostly I am taking these four and I will elaborate one by one. First, electromagnetic damping. So here you can see, once try to recollect the moving coil galvanometer concept. So I showed the moving coil galvanometer while explaining the topic. So once again, if you see, so moving coil galvanometer, if you open inside, you can see the coil, and inside the coil you can see one metal drum, cylindrical drum. So here cylindrical drum is there, and it is wounded by a coil. So whenever current passes in it, due to the current carrying coil in external magnetic field, torque will generate. Due to the torque it will move. So conductor moving in external magnetic field, so ED currents will develop. That ED current try to stop the rotation of the conductor. So that is why, so whenever you apply the current, actually if that electromagnetic damping not there, means restriction to rotation of the body in magnetic field. So that is electromagnetic damping. So due to the induced current, the damping is coming, means the body is getting the restriction to the motion due to ED current. So that is electromagnetic damping. So damping means restriction to the motion. So that is we are getting due to ED current. So whenever current passes through the coil, immediately it will get the twist. So due to the twist it will turn, but actually it has to vibrate continuously with small amplitude. Also we can't identify the exact reading. So for that purpose it has to take rest immediately. So to come to rest immediately means it has to show immediate reading. So we are arranging one conductor cylinder inside. So due to the current, ED current will develop. That ED current try to stop the coil rotation, so that it will be stopped at a fixed point immediately. Means it will not make number of oscillations, it will make just half of the oscillation, that we are calling as dead beat. Means just one side oscillation it will be stopped. So due to electromagnetic damping we able to measure the reading easily. If not, if it is not there, it will vibrate continuously, then we can't measure the exact reading. So by ED currents we are developing electromagnetic damping, and we are arranging the needle at a fixed position. So this is the one of the advantage of ED current. Next, induction furnace. So one more advantage, fuse AC current if you pass, then heat currents will develop. That heat current creates the heat to the conducting material. So by arranging AC current here, we can create heat current. Due to heat current here, we will get the more amount of heat. So if you are not feeling this is as a stove, I will show one more. See here, down, this is a metallic pot, and as well as this is the metallic plate. Down, if you arrange the varying magnetic field, that varying magnetic field produces the heat currents on the conductor, then conductor will get heat. That heat taken by these bowls, and those bowls easily become warm, and we can use this concept for cooking. Means that entire one used as a stove. Okay, so that is simply induction furnace. So here, by giving more amount of AC current, we can generate huge heat in such a way that we can melt the metal also. So that is why this one industrial applications also there, to separate the ore, means to separate the metal from the ore. Sometimes in some cases they are using induction furnace industrially. Next, electric power meter. So presently we are upgraded digital meters we are using, but olden days, whether you know or not, so if you have nearby any old house, I think at every place they replaced with old meters. Means new meters are replaced, old meters not there now. So old meter, just if you observe, so inside you can see one aluminum drum. So it's a conducting drum. So whenever current passing, means whenever you are using the current, then so due to that current here on this drum, heat current will develop. Due to that it will get rotation. So due to the number of rotation here, it will show the reading. So 10 number of readings, just 0.1 unit, and 1000, then it will be 1 unit. So like that, that calibration, and what it may be, simply whenever you are using the current, then heat current will develop. Due to that it will get rotation. So with respect to that, we are measuring the reading, that is voltmeter phenomena. Next, magnetic braking. So it is an excellent concept, and path braking, and as well as next coming technology, definitely they will use this type of one. So once observe, for example, it is an electric train for suppose. So for these wheels, there is no braking system directly. Means old braking system means one foot will be there. So whenever driver want to stop the vehicle, they will apply the brake, then the rubber foots will come in contact with the wheels. But that is a risky one at high speeds due to more amount of heat. So friction will develop. Means due to more rotation, whenever we are making it into contact at a high speed, the wheel and the bush will get more amount of heat. Due to that, maybe there is a failure for the brake, but without touching the wheel, here we can stop the vehicle just by applying heat current. So here the technology, they will apply more magnetic field to the conductor. So here the conductor is in rotation. Whenever we want to apply the brake, we will apply more strong magnetic field. Then the strong magnetic field don't allowed by the conductor, so the conductor will try to stop the external magnetic lines of force. So with respect to that, it will try to stop. So it will try to stop the magnetic field. So with respect to that, heat currents will generate. Those will try to stop the rotation of the wheel. So vice versa. So what it may be, we are getting the advantage here. So magnetic field applied to the rotating wheel, then the rotating wheel will try to stop the magnetic flux. So in reverse case, so here the rotation speed decreases. So how much magnetic flux we are applying, that much force will add to the drum to stop that one. Next, heat current energy loss. So here so far we discussed the advantages, but we can analyze in this way also. So here heat current, for example I, then I square R amount of heat developed, that means this much power will develop. However, I square RT heating from heat current cause causes energy loss. So if we do not want energy loss, you probably think ED current are bad. Means if you think that is as an advantage, it's fine. If not, in general, due to ED current, I square or heat is developing, due to that is the energy loss that we can analyze in this way also. So undesirable effect of ED current means, according to simple point of view, so ED currents are produced inside the iron core of a rotating armature of electric motor. So electric motor means inside coil, armature means it's a coil, two-dimensional coil. It will rotate. It's a separate shape of coil, so it is rotating. So definitely ED current, conductor moving in magnetic field, so ED current will develop. So dynamo coil moving in magnetic field, ED current is there. And transformer core, so transformer is working with AC, so that core is having metal. So due to that, ED current will develop there also. So whenever ED current coming, there is a heat. I square R amount of power is generating, means heat. In the form of heat we are losing the energy. So if it is small one, fine. But if it is at a large scale, then due to that cause unnecessary heating and wastage of power. In some cases the heat produced is high. The ED currents may even damage the insulation of coils also. So there is a damage due to ED currents, but advantages also there. It is like friction. It is a necessary evil. So here also ED currents, there is an advantage. If you can overcome the ED currents, advantages we can take.
Namaste students, welcome to physics class. In class 11 you learn about inertia, means the body does not want to change its state in rotating motion. In linear motion, that we are calling as mass. The same inertia is there in electrodynamics also, that we are going to learn in this video.
Before going to the theoretical explanation, once observe the diagram. So here one wire wounded with some number of turns and arranged as a particular length. So this one, what you are observing, it is called as a coil or solenoid. So it will have generally uniform cross section. Now before going to the theoretical analysis of this solenoid or self-induction, I want to ask a few questions. If you observe any electrical device which is operating with a remote or generally with a LED indication, whether it is on or not, so that one, whenever you switch on the device, immediately that bulb will not be switch on, it will glow slowly. As well as whenever if you switch off the device, that LED bulb immediately will not switch off, slowly it will off, means the intensity of the light coming out of that LED decreases and finally it will become zero. Why it is happening like this? The reason you will come to know in this video. So our topic is self-induction. Self-induction in the sense, if a coil is there in a particular electrical circuit, if you try to pass the current in the circuit, then the coil will not allow the growth or change of current. That phenomena is called self-induction. So that what I mentioned initially, it is electromagnetic inertia. Don't like to change. If it is increasing, means if current increasing, it will try to oppose. If current decreasing, then also it will oppose. So for clear analysis, I want to give one circuit now. So let a coil XY be connected to a battery through a tapping. When the key is not present, so in the circuit you can see, for example, key is not present, then there is no electric current flows through the coil. So no magnetic flux is linked with the coil. So in that case, there is no current, there is no change of current, then there is no story of opposing. But if you connect the key, means if you tap the key, then So whenever if you tap the key, current will start flow through the circuit. Then an induced EMF will develop inside the coil and it will try to oppose the growth of current. If you untap the key, then current will decreases. Then also it will try to oppose the decreasing. So here it don't like to change. So that is only generally in mechanics we are calling as inertia. The body doesn't want to change its state. So here the coil doesn't want to change the flow of current in it. The phenomena is called self-induction. So the coil itself it is having. So that is why we are calling that is as self-induction. Why I am telling here, one more is there, that is mutual induction. We are going to learn in the next topic. So here, if you draw a graph by taking time and current in the coil, x-axis time and y-axis current, you will observe the graph like this. Whenever you switch on the device, immediately current will not increase to maximum value. Slowly it will increase and it will become maximum value. Why? Because whenever you try to allow the current in the circuit, if the coil is there or solenoid is there, then that coil try to oppose the growth of current. So that is why slowly current will develop and it will become maximum. Then afterwards if you switch off, so it will become maximum, afterwards it will be a straight line. But if you switch off, so after AC onwards, for example, if you switch off, then immediately current will not be zero. Some amount of current will be stored inside in the form of energy. So in the form of magnetic field, energy will be stored in the solenoid. So that energy will come out as a current. So slowly current decreases and will become zero. Now apply this current process to the LED. So whenever you switch on the device, immediately current will not go to the LED. So slowly current will develop in the circuit. So whenever sufficient current comes to the LED, then only LED will glow. So slowly LED will glow. If you switch off, immediately LED will not off. So it will take time. Slowly it will become dim and it will be intensity will be zero. So reason, inside the coil some amount of energy will be stored. Generally in the device the coil concept will be there. Why? Because most of the electrical home appliances will have coil. So if there is a transformer, so AC to conversion into low voltage AC, so definitely there will be a transformer. General home appliances will not be operated at 240, so for that purpose we will use step down transformer. So with respect to the step down transformer, coil will be there, primary coil, secondary coil. So this coil and self-induction, mutual induction concept involved in it. So those details, transformer details, we will discuss in the next lesson. Transformer is the next lesson topic. But here in home appliance, that coil will be there. So due to that energy will be stored. So that energy, even though if you switch off, the energy will come from the coil. So due to that LED will go a little bit extra time even though you switch off the device. Now theoretical analysis. Definition first. This phenomena in which the coil opposes any change in current flowing through it by inducing an EMF in itself is called self-induction. So it's a property of the coil. So it will try to oppose the current by developing EMF in it. So induced EMF will develop. So induced EMF developed means magnetic flux will develop in the coil. So as current passing in the coil means there is a magnetic flux. So magnetic flux linked with the coil is there. Here self-induction is the phenomena of production of an opposing induced EMF in a coil as a result of varying current in the coil, as a result of varying current in the coil itself. Next, mathematically particular magnitude wise we can represent, means how much quantity of opposing. So for that purpose, means generally physics means any concept we will try to measure as a particular quantity, as a physical quantity. So the physical quantity quotient of self-induction means a coil of a number of turns, it will have certain amount of quantity of opposing sense. So that we will measure as a concept of quotient of self-induction. So let us introduce. So let phi be the magnetic field when the current I flows through it. So when our current passing, there is a flux. So that magnetic flux proportional to current. If current is zero, then there is no magnetic flux in it. So as much as current if you pass, that much magnetic field develop in the coil, that we learned already in the previous class. So magnetic flux proportional to current strength. More current, more magnetic flux. So there is a proportionality. The proportionality constant is called L. That L proportionality constant that we are calling as self-inductance or quotient of self-induction. For example, if current passing through the circuit is 1 ampere, then how much flux developed in the coil, that is numerically equals to the self-induction or quotient of self-induction. Once again, definition. The self-inductance of a coil is numerically equal to the magnetic flux linked with the coil when unit current flows through it. So phi equals to Li. If current value is 1, then self-inductance equals to flux. Now further analysis. If you differentiate this equation, what you will get? Flux phi equals to L into I. If you differentiate with respect to time, then d phi by dt equals to L. It's a constant, proportionality constant into di by dt. So if there is a change in current, so then there is a change in flux. So we know that according to Michael Faraday, the change of flux induces EMF. So the variation in current inducing the EMF, so that is why EMF equals to minus d phi by dt according to Faraday. So now instead of d phi by dt we can write E. So therefore E equals to minus L into d phi di by dt. So here the negative sign indicates the EMF current both are in opposite direction. So magnitude wise E equals to L into di by dt. So from this we can define self-induction or quotient of self-induction or self-inductance. So first, we know from the previous equation L equals to, we can write E by di by dt. It's numerically. Now for suppose the rate of flow of current is 1 unit for suppose, then the EMF induced is numerically equals to self-inductance. Now further we can define the self-inductance of a coil is defined as the numerical value of self-induced EMF, but condition when current varying in the rate of 1 unit is passed through it. If rate of change of current is 1 unit, then self-induced EMF developed numerically equals to self-inductance or quotient of self-induction.
Namaste students, welcome to physics class. Through this video you are going to get the recap for self-inductance and as well as derivation for quotient of self-induction due to a long solenoid.
Before going to the theoretical explanation, once observe the diagram. So here one wire wounded with some number of turns and arranged as a particular length. So this one what you are observing, it is called as a coil or solenoid. So it will have generally uniform cross section. Now before going to the theoretical analysis of this solenoid or self-induction, I want to ask a few questions. If you observe any electrical device which is operating with a remote or generally with a LED indication, whether it is on or not, so that one, whenever you switch on the device, immediately that bulb will not be switch on, it will glow slowly. As well as whenever if you switch off the device, that LED bulb immediately will not switch off, slowly it will off, means the intensity of the light coming out of that LED decreases and finally it will become zero. Why it is happening like this? The reason you will come to know in this video. So our topic is self-induction. Self-induction in the sense, if a coil is there in a particular electrical circuit, if you try to pass the current in the circuit, then the coil will not allow the growth or change of current. That phenomena is called self-induction. So that what I mentioned initially, it is electromagnetic inertia. Don't like to change. If it is increasing, means if current increasing, it will try to oppose. If current decreasing, then also it will oppose. So for clear analysis, I want to give one circuit now. So let a coil XY be connected to a battery through a tapping. When the key is not present, so in the circuit you can see, for example, key is not present, then there is no electric current flows through the coil. So no magnetic flux is linked with the coil. So in that case, there is no current, there is no change of current, then there is no story of opposing. But if you connect the key, means if you tap the key, then so whenever if you tap the key, current will start flow through the circuit. Then an induced EMF will develop inside the coil and it will try to opposes the growth of current. If you untap the key, then current will decreases, then also it will try to oppose the decreasing. So here it don't like to change. So that is only generally in mechanics we are calling as inertia. The body doesn't want to change its state. So here the coil doesn't want to change the flow of current in it. The phenomena is called self-induction. So the coil itself it is having, so that is why we are calling that is as self-induction. Why I am telling here, one more is there, that is mutual induction. We are going to learn in the next topic. So here, if you draw a graph by taking time and current in the coil, x-axis time and y-axis current, you will observe the graph like this. Whenever you switch on the device, immediately current will not increase to maximum value. Slowly it will increase and it will become maximum value. Why? Because whenever you try to allow the current in the circuit, if the coil is there or solenoid is there, then that coil try to oppose the growth of current. So that is why slowly current will develop and it will become maximum. Then afterwards if you switch off, so it will become maximum, afterwards it will be a straight line. But if you switch off, so after AC onwards, for example, if you switch off, then immediately current will not be zero. Some amount of current will be stored inside in the form of energy. So in the form of magnetic field, energy will be stored in the solenoid. So that energy will come out as a current. So slowly current decreases and will become zero. Now apply this current process to the LED. So whenever you switch on the device, immediately current will not go to the LED. So slowly current will develop in the circuit. So whenever sufficient current comes to the LED, then only LED will glow. So slowly LED will glow. If you switch off, immediately LED will not off. So it will take time. Slowly it will become dim and it will be intensity will be 0. So reason, inside the coil some amount of energy will be stored. Generally in the device the coil concept will be there. Why? Because most of the electrical home appliances will have coil. So if there is a transformer, so AC to conversion into low voltage AC, so definitely there will be a transformer. General home appliances will not be operated at 240, so for that purpose we will use step down transformer. So with respect to the step down transformer, coil will be there, primary coil, secondary coil. So this coil and self-induction, mutual induction concept involved in it. So those details, transformer details, we will discuss in the next lesson. Transformer is the next lesson topic, but here in home appliance that coil will be there. So due to that energy will be stored. So that energy, even though if you switch off, the energy will come from the coil. So due to that LED will go a little bit extra time even though you switch off the device. Now theoretical analysis. Definition first. This phenomena in which the coil opposes any change in current flowing through it by inducing an EMF in itself is called self-induction. So it's a property of the coil. So it will try to oppose the current by developing EMF in it. So induced EMF will develop. So induced EMF developed means magnetic flux will develop in the coil. So as current passing in the coil means there is a magnetic flux. So magnetic flux linked with the coil is there. Here self-induction is the phenomena of production of an opposing induced EMF in a coil as a result of varying current in the coil, as a result of varying current in the coil itself. Next, mathematically particular magnitude wise we can represent, means how much quantity of opposing. So for that purpose, means general physics means any concept we will try to measure as a particular quantity, as a physical quantity. So the physical quantity quotient of self-induction means a coil of a number of turns, it will have certain amount of quantity of opposing sense. So that we will measure as a concept of quotient of self-induction. So let us introduce. So let phi be the magnetic field when the current I flows through it. So whenever current passing, there is a flux. So that magnetic flux proportional to current. If current is 0, then there is no magnetic flux in it. So as much as current if you pass, that much magnetic field develop in the coil, that we learned already in the previous class. So magnetic flux proportional to current strength. More current, more magnetic flux. So there is a proportionality. The proportionality constant is called L. That L proportionality constant that we are calling as self-inductance or quotient of self-induction. For example, if current passing through the circuit is 1 ampere, then how much flux developed in the coil, that is numerically equals to the self-induction or quotient of self-induction. Self-inductance of a long solenoid. To get an expression for the self-inductance of a particular solenoid or coil, consider a solenoid having n number of turns, and L is the length of the solenoid and number of turns per unit length, nothing but capital N by L, n capital N number of turns and small n is number of turns per unit length. For suppose I is the current passing through the solenoid and it is having uniform cross section for suppose capital A, then the magnetic field B inside the solenoid is, so that magnetic field expression, so we don't have in syllabus, so direct expression, that is B equals to mu naught Ni, means magnetic field inside the current carrying solenoid, that is at inside point, not outside point, not at the end point. So at inside, Means if you consider it is a long solenoid, then at any inside point, that is uniform magnetic field, that is mu naught Ni. So here instead of small n, we can write capital N by L, number of turns per unit length, that is capital N by L. Then we can also write mu naught capital N I by L. Now if you know the magnetic field, magnetic flux we can express, that is magnetic flux through the solenoid, that is phi equals to B into A according to the definition. Then instead of B we can write mu naught Ni by L. So the flux phi equals to mu naught Ni by L into A. Now total magnetic flux linked with the solenoid. So here for one turn flux phi, if there are n number of turns, so that is flux linked with one turn. So if there are n number of turns, n into phi. So that we already discussed in Faraday law also. So n into the flux what we analyze, that is mu naught Ni by L into capital A. So n into n square. So that is why mu naught n square I by L into A. But our aim to analyze the quotient of self-inductance for the coil or solenoid. If L is the quotient of self-inductance of the solenoid, then according to the definition of solenoid, the flux linked with the coil due to current is proportional to current. So the proportionality constant is quotient of self-induction. So now n phi is the total flux linked with it. So instead of Li, n phi, so that we can write directly this expression. So therefore Li equals to, instead of n phi, I'm writing mu naught n square I by L into A. Now if you observe both sides I we can get cancelled, then the quotient of self-induction for the solenoid L equals to mu naught capital N square A by L. So this is the expression of one kind. Now we can modify further. Instead of small capital N, means it is in terms of capital N, we can obtain the expression in terms of small n also. So for that purpose we can change the expression, but before that, from this we can say directly self-inductance is proportional to square of the number of turns. So it depends upon number of turns, depends upon area. If area is bigger, more cross-sectional area means more self-induction it will offer, means it can store more amount of energy, and inversely proportional to length. So directly proportional to square of the number of turns, directly proportional to cross-sectional area, and inversely proportional to length. For most of the problems we will use L proportional to n square, so that is why I'm highlighting this one. Now the expression in another way, so n small n, nothing but capital N by L. So therefore instead of capital N we can write small n into L. If you substitute this one in the above expression, instead of capital N, small n into L whole square, nothing but small n square, small L square. So square L get cancelled. So therefore quotient of self-induction for a long solenoid L equals to mu naught small n square A L. This is the expression in terms of number of turns per unit length. Now inductors in series and parallel combination, as like resistors. For example, two resistors connected in series or two resistors connected in parallel. What will happen? We know already. Two resistors connected in series in lower classes you learn. If you connect two resistors are in series, resultant resistance increases. If you connect two resistors are in parallel, resultant resistance decreases. For example, R1, R2 resistors connected in parallel, then resultant resistance 1 by R equals to 1 by R1 plus 1 by R2. But in this case, what will happen? So for that purpose, first, inductors are in series. If you connect like this, so both are connected in series, means as like resistors, those also will follow the same resultant resistance L equals to L1 plus L2. Okay, so here mutual induction effect also will be there. You will study in different books something additional expression, but so far we did not discuss that one, so that is why I'm limiting to only self-induction. In next coming classes I will upgrade the remaining expression also, but approximately we will consider this expression only to solve the numericals, that is L equals to L1 plus L2. Now, if these two inductors are connected in parallel, so inductors are in parallel according to the diagram, then resultant, as like resistors connected in parallel, resultant resistance decreases. Similarly here inductance also decreases, self-induction decreases. So 1 by L equals to 1 by L1 plus 1 by L2. One example problem. What is the self-inductance of a solenoid of length 40 cm, area of cross section 20 cm square, and total number of turns 800? So if you take the given data, so length L, if you consider L, small l, 40 centimeter, nothing but 0.4 meter. Here centi means 10 to the power of minus 2, so 40 into 10 to the power of minus 2, nothing but 0.4. Here compulsory we have to convert it into SI system. Why? Because the self-inductance unit is Henry, that is SI system of unit, so that is why all physical quantities should be in SI system. So length small l we considered, so that is given 40 centimeter, and cross sectional area capital A, that is 20 centimeter square. So centimeter square means centi square meter square. So centi 10 to the power of minus 2, centi square means 10 to the power of minus 4. So 20 into 10 to the power of minus 4 meter square cross sectional area, and number of turns they mentioned 800. So capital N 800. It's the only number of turns, not number of turns per unit length. So that is capital N 800 mentioned. So L value they're asking. So according to the formula, L equals to mu naught N square AL. So here mu naught is the constant permeability of the free space that we have to remember. Mu naught equals to 4 pi into 10 to the power of minus 7. So if you substitute, L equals to 4 pi into 10 to the power of minus 7 into number of turns 800, so 800 square, into capital A, area 20 into 10 to the power of minus 4, by L, length of the solenoid or coil, 0.4. So if you simplify the entire expression, then you will get simple answer, that is 4.02 into 10 to the power of minus 5. So this is the answer for the entire solenoid. Mutual inductance. Before going to the topic of mutual induction, once a small recap of self-induction. So self-induction means if a coil is connected in a circuit, if current passing through it, then whenever if you switch on the key, current will start growing in the circuit. But this coil don't like to change the current, nothing but if current increasing in it, it will oppose. If current decreasing, it will oppose. So the opposing property to the growth of current in the circuit by itself means inside the solenoid, when current passing in it, if it is happening, means it opposing a coil. If current passing through it, inside the coil, if something opposing induced EMF develops to stop the growth of current, that is self-inductance. But mutual inductance means that is between the two coils. For suppose the flux linked with one coil is changes, means for example two coils are very near. In one coil, for suppose there is a growth of current, then induced EMF will develop in opposite direction nearby another coil, that is the second coil, or generally we will call as secondary coil. It try to opposes the growth of current in the first coil. So this is between two coils. So that is why we are calling this is as mutual induction. So inside the same coil, something developing, that is a self-induction. Nearby coil, the opposing self-induction means opposing induced EMF, that we are calling as mutual inductance, the phenomena. Now definition wise, mutual induction between two coils is defined as the property of the coil due to which it opposes the change of current in the other coil. So if current passing in one coil, for example, increasing, it don't like to increase, it don't like to decrease. The phenomena developing in nearby coil that is mutual inductance. So based on this principle, transformer working. For suppose it's a primary coil and nearby you arranged another coil. So here huge voltage, for example, is there. Then if you arrange less number of turns, then here voltage will be more, but here less voltage you will get. So the transformer can convert high voltage to low voltage. For suppose here less number of turns, in secondary coil more number of turns, then more voltage will develop in the second coil. So that is called step up transformer. In next coming topics you will come to know the details about the transformer, but presently according to the transformer, this is primary coil, this is secondary coil. So in primary coil more number of turns are there, and in secondary coil less number of turns, voltage decreases, and vice versa. So transformer working based on the principle of mutual inductance. Now quotient of mutual induction, that one expression. So for that, for suppose in a circuit one coil is there. Whenever if you switch on the current, whenever if you allow the growth of current in one coil, so nearby another coil current will develop, induced EMF will develop in the secondary coil. S means secondary coil, P means primary coil. So that we can trace out, means we can identify through galvanometer. Now for suppose in primary coil current is I1, then in the secondary coil EMF will develop, means current will pass in it. Due to that, in secondary coil EMF will develop. So with respect to that, it's a current carrying coil, magnetic flux will develop. So magnetic flux in the secondary coil, for example phi 2, there are n number of turns, so n phi 2, then the flux developed in the secondary coil is proportional to current in the primary coil. In primary coil current is 0, then there is no effect. If more current passing through it, then more EMF and more flux will develop in the secondary coil. So the proportionality constant between the flux and current we are calling as quotient of mutual induction. So the quotient of mutual induction we can write as M equals to N2 phi 2 by I1. Now to define the quotient of mutual induction, for suppose current expression is there in the denominator, for suppose the value is 1. If I1 is 1, then simply the expression will be M equals to N2 phi 2. So now with respect to this equation we can define simply the quotient of mutual induction. That is, quotient of mutual induction of two coils is equal to the number of magnetic flux linkages in one coil when a unit current flows in the other. So for example, the other means the first coil. In the first coil, for example, current is 1, then the flux linkage in the second coil is numerically equals to the mutual induction. According to Faraday's law, the EMF developed is proportional to rate of change of flux. If there are n number of turns, then into n. So the total flux is N2 phi 2. So therefore EMF induced in the secondary coil E2 equals to minus N2 d phi or delta phi 2 by delta t. So now that N2 we can write inside also. Now just now we analyzed N2 phi 2 means, that is Mi1. So if you substitute that one, then EMF developed in the secondary coil is equals to minus delta Mi1 instead of N2 phi 2 by Mi1 by delta t. So now M we can write outside, then minus M into delta I1 by delta t. This one we can also write minus M into di by dt also. Now from this expression also we can define quotient of mutual induction. So here the mutual induction M equals to, we can write E2 by delta I1 by delta t. Now from this expression, if the denominator rate of change of current is unique, means unity, then suppose in this expression the denominator is equals to 1, rate of change of current, then EMF developed in the secondary coil is numerically equals to mutual inductance or quotient of mutual induction. So that we can define like this. The SI unit of quotient of mutual induction and as well as self-induction both are same, that is Henry. Thus, according to the expression, the mutual inductance of two coils is 1 Henry when an induced EMF of 1 volt is set up in one of them due to the current changing at a rate of 1 ampere per second. So if 1 ampere per second current change is there, which is equals to 1 ampere per second, then the EMF developed in a nearby coil is the mutual induction between the two coils. So 1 Henry we can write, which is equals to 1 volt by 1 ampere per second. Mutual inductance of two long solenoids. This is very important topic. Sometimes we may get this one in essay question also. For suppose one coil S1 is wounded like this. On this another coil is wounded, for suppose that is S2. In first coil current is I1, in second coil current for suppose I2, and as well as the length of the coils for suppose L, so both are having same, and radius of first one is R1, radius of second one is R2 for suppose. Then we want to develop the expression for mutual inductance between the two coils. So if current passing in one coil induces the current in another coil. Okay, so for example in primary coil there is a current growth, so due to that induced EMF will develop or induced current will develop in the secondary coil. For suppose if you consider that one, the flux developed in the secondary coil or second coil due to the first coil. Here 5 to 1 means flux developed in the second coil due to the current in the first coil is proportional to current in the first coil. Okay, now simply the proportionality constant M21 is called quotient of mutual induction between them. So now further, the magnetic field developed inside for a solenoid, that is mu naught N1 I1. For example, I1 is the current passing in the solenoid, then magnetic field, uniform magnetic field developed inside the coil is mu naught N1 I1. Now from this simply we can say magnetic flux. So magnetic flux linked with each turn of the solenoid. So here so far we said just only flux, but this is for each turn. That means so S2 means in the second coil the flux linked is equals to magnetic field into area. So for example capital A is the cross sectional area of the coil, second coil. Then so generally one is wounded on another, so both approximately same. So A is the cross sectional area. Then B1 magnetic field into area is the flux linked with each turn of the solenoid. Then therefore total magnetic flux linked with the solenoid S2 will be, so just now we discussed the flux linked with one turn, that is B1 into A. For example there are two turns, then 2 into B1A. For example there are 3 turns, 3 into B1A. If there are n turns, n into B1A. So here the flux nothing but B into A into total number of turns. But here total number of turns we did not define so far. For suppose N1 number of turns per unit length for first coil, for example primary coil, and as well as N2 number of turns per unit length in the secondary coil. So then so here number of turns per unit length, if you multiply with length you will get the total number of turns. These are the total number of turns in the second coil. Now the total number of turns into B into A, actually B1 is the magnetic field we considered. So B1 means magnetic field due to the first coil into A, total cross sectional area and number of turns. This is the total flux in the second coil. Now instead of B1, if you substitute mu naught N1 I1, so N1 number of turns in the primary coil. Now if you reshuffle and if you write N1 N2 at one place, so mu naught N1 N2 A into I1 into L. But the total flux according to quotient of mutual induction we can express like this: total flux equals to mutual induction into I current passing in it, that is actually I1 current passing in it. Now both sides I1 if you get cancelled, then quotient of mutual induction between the two coils equals to mu naught N1 N2 AL. So this is with number of turns per unit length. Now if you substitute instead of N1 and N2, capital N1 N2 means only number of turns, then the expression will come in terms of N1 and N2. But before that, so small analysis. Here one coil is wounded on another coil. So mutual induction developed in one coil. If current passing in one coil, another coil it will develop. Similarly, if current passing in the second coil in the primary coil also it will be same. Means current passing in one first coil, induced EMF will develop in the second coil. If current passing in second coil, induced EMF will develop in the first coil, and both will be same. So M12 equals to M21. So here M21 so far we analyzed mutual induction means flux developed in the second coil due to current in the first coil. Similarly, flux developed in the first coil due to current in the second coil. So that also if you analyze it will get the same. So let it be capital M. So instead of mentioning M12 or M21, so directly we can mention as capital M. In that case, M equals to mu naught N1 N2 AL. Now instead of N1 and N2, if you write N1 by L and N2 by L, here length we consider same. So in that case, so instead of N1 small n1 capital N1 by L, instead of small n2 capital N2 by L. So now L get cancelled, as well as instead of area. So for example, one is wounded on another. So instead of mentioning R1 R2, so both are having same radius, we can mention only R or only R1. So then area of the coil, cross section area of the coil, that is pi R1 square. Then L get cancelled, the expression will be like this. So mu naught N1 N2 by, so one L get cancelled, so only one L left out. So here we can mention in terms of radius also, or as it is A. So now from this expression you can say quotient of mutual induction depends upon few factors. Here depends upon number of turns, depends upon cross sectional area, and as well as mu naught. So these details if you mention as points, the quotient of mutual induction between two coils depends upon size of the coils. So for example, area is bigger, then the quotient of mutual induction or simply mutual inductance will be more, as well as depends upon their shape. If you change the shape, then induction will change, and depends upon number of turns. So here you observed in the equation, mutual induction is proportional to N1 and as well as proportional to N2. So product of number of turns. So if you increase one number of turn, then large difference will come in quotient of mutual induction. Next, nature of material on which two coils are wounded. So here in the expression mu naught is the permeability of the free space mu naught. But if you introduce a medium, then the medium permeability is high, then mutual induction also will be high. So if you introduce any soft iron material, then if small current passes, flux will develop, magnetic flux. Due to the small magnetic flux, the iron will become strong magnet, so that more flux will develop immediately. So more quotient of mutual induction the coil will show. Means more opposing effect, means more EMF will develop in the second coil due to the soft iron inside. Instead of air core, if you introduce any iron core, then the effect will be different. That means it depends upon nature of material which we are wounding, on which we are wounding the coil. Next, distance between the two coils. This is also very important. If coils are completely separated, then there is no effect of mutual induction. Both should be very near. Then only the effect of mutual induction will be there. So these are the major points we have to mention according to the equation we derived. Torque on a rectangular current carrying loop in uniform magnetic field. So consider a rectangular coil in uniform magnetic field as shown in figure. If you pass the current through this rectangular coil in any direction as shown in the diagram, so clockwise or anti-clockwise, so here according to the diagram clockwise, so definitely there will be a torque will be there on the current carrying coil. So here for the torque expression already we learned in the previous class, moving charges and magnetism lesson. So that is why the direct expression what we know. So the torque acting on the coil is proportional to current and proportional to cross-sectional area of the coil and as well as magnetic field and sine of the angle between normal to the coil and as well as magnetic field. For suppose there are n number of turns to the coil. For suppose this coil consists of n number of turns, then the flux will be n times as well as the torque will be n times. So that is the torque tau equals to NIAB sin theta. So now further we can short out this equation as MB sin theta. So here M nothing but N into I into A. So that is also called as magnetic moment of the coil. Here torque tau equals to mb sin theta, so we can write as a vector notation, that is tau bar equals to m bar cross b bar. Now in the next coming topic, AC generator, we will apply the torque and we can generate the electricity. It is the reverse effect, means here we are passing the current and we are getting the mechanical work, but if you do the mechanical work then current will be generated. So it's a vice versa. So we are going to learn and how to design the AC generator to get the electrical energy from the mechanical work. So the topic is AC generator. So AC generator produces electrical energy from mechanical work. The principle behind the topic is based on the electromagnetic induction, so which states that whenever magnetic flux linked with the coil changes, there is an EMF induced in the coil. It is a Faraday's law. So according to the Faraday's statement, it is the practical application. The main parts of an AC generator as shown in the diagram. So here you can see number of parts. So let me explain one by one. The first one, armature. So armature nothing but it is a coil. So maximum they will take identical number of turns, means n number of turns all are identical one coil. So that we are calling as armature, which can rotate freely about an axis. They will arrange in between the pole magnets. So it is a rectangular armature, is the rectangular coil. You can see A, B, C, D. So consists of large number of turns of copper wire. Generally copper we will use, wound over the soft iron. Core is called armature. So why we are using soft iron? There is a reason. So if it is air core, means only air is there, then magnetic flux strength will be less. If you use the iron, due to the retentivity of the iron material, more magnetic flux will be there to the coil and that will change, so which leads to more EMF. So to get the more EMF, we can use the soft iron to increase the strength of the magnetic field to the coil. Next, field magnets. You can see north pole and south pole. So external magnetic field, this should be uniform. So whenever it is rotating continuously, the same amount of magnetic field should act. So two pole pieces of strong electromagnet. So generally we will use magnets or to get strong magnetic field, we are using electromagnets also. That is depends upon the purpose. Next, slip rings. You can see here R1, R2, two rings. So continuously one ring will be connected to one end of the armature or coil, and other end will be continuously connected to ring R2. So these two we are calling as slip rings. So the end of the coil ABC are connected to two hollow metallic rings R1 and R2. Those we are calling as slip rings. So as the coil is rotating continuously, even though the coil one end continuously will be in contact with one metallic part that we are calling as brush B1, and another one is connected to ring R1, or another one is connected to ring R2, so which is connected to the brush B2. So let me explain those brushes details. B1, B2 are those are flexible metal plates of carbon rod. They are fixed to the rings R1 and R2, so continuously they will maintain the contact. So here we are generating the AC. So AC nothing but alternating current. So why it is an alternating current? So here we are rotating this one, mechanical work we can do, but here we will get alternating current. For mechanical work we will get alternating current. So here alternating current means continuously polarity will change. Reason, for suppose here whenever we are rotating this one, so here current direction will be in one direction, but whenever it is going up to here, so then current direction will change. So in the same magnetic field, for suppose AB end is here, for suppose current passing from A to B, then whenever we are rotating this one here, so then it will come in opposite direction. So here A to B, so whenever that AB comes here, it will come in this direction. So here if you consider the direction, it is clockwise. Whenever it is here, so current passing from A to B, then that time it will be in anti-clockwise direction. So the direction of current changing, nothing but continuously polarity is changing. So as the direction changes, that we can treat as a polarity. So positive negative peaks continuously. So as we are rotating with uniform angular velocity, then fixed frequency alternating current will be generated across the resistor. That output will be alternating EMF or alternating current. Next, theory and working. For suppose the coil is rotating in a uniform magnetic field, for suppose at a particular time, at a particular instant, it is making an angle theta with the magnetic field direction. For suppose this is the magnetic field direction, north to south, and the normal to the coil is making an angle theta with the magnetic field at that time. So to get the EMF, so how much EMF will generate, what are the factors affecting the EMF, to know that one, so just to calculate the magnitude of EMF induced here at a particular instant, so consider A is the area of the coil and N number of turns in the coil, and B is the magnetic field strength acting here on the coil, and as well as at a particular instant theta is the angle which is making with the normal to the coil. It's a very important point. This is not the angle between the plane of the coil and magnetic field. It is the angle between normal to the coil and as well as magnetic field. So then the magnetic flux linked with the coil in this position we can write as phi equals to N into BA. For suppose there is only one turn, then flux phi equals to B into A. For suppose there are n number of turns, so flux will be n times, so N into B into A. So here A and B are vectors, so we can go for dot product, so that is AB cos theta. So here theta we can express in terms of angular velocity. So angular velocity nothing but angular displacement by time. So theta equals to angular velocity into time. So angular velocity nothing but angular displacement by time. So theta angular displacement equals to omega into t, angular velocity into time. So instead of theta, if you substitute omega t, then the expression for the flux will be NBA cos omega t. So this is the flux. So as we are rotating the coil, continuously the flux will change. that depends upon angle theta. If theta is 0, then maximum flux will pass through the coil. If theta is 90 degrees, then zero flux will pass through the coil. For suppose the normal is making angle 90 degrees with the magnetic field direction like this, then flux passing through the coil will be 0. So different angles will be there, so accordingly the flux will change. Now as flux changes, EMF induces, that is Faraday's law. So according to Faraday's law, that we can analyze EMF induced in the coil, so that is E equals to minus d phi by dt, that is Faraday's second law. For suppose n number of turns n phi, so that we already considered flux phi equals to nba cos omega t. If you substitute instead of flux the entire expression, so then EMF E equals to minus into d by dt of, instead of pi, NAB cos omega t. So here n constant, a constant, b constant. So the differentiation for only cos omega t. So cos omega t and differentiation omega into, so here first cos omega t differentiation minus sin omega t, and as well as omega t differentiation omega y, because we are doing with respect to time. So the expression will be, so minus as usual NAB into d by dt of cos omega t. Now if you differentiate, then instead of cos omega t on differentiation, it will become minus sin omega t, and omega t differentiation omega. So minus and minus get cancelled in the multiplication. So the final expression will be NAB omega into sin omega t. So here EMF depends upon the angle theta and as well as time. So here many factors affecting the EMF induced in the coil. So that depends upon number of turns. If number of turns are high, then EMF induced will be high. If cross sectional area is high, in that case also EMF induced will be high, and as well as it depends upon the magnetic field, uniform magnetic field strength what we are arranging, that is, and as well as omega. How much you rotate, that much EMF will generate. But this will be fixed. Why? Because if you want to use AC, so according to India, that frequency should be 50 Hz. So that is why we should not cross. So infinite mean, or whatever we want, that much we can't generate. If you want to use for whole purpose, so compulsory here frequency should be 50. So angular frequency according to the value. So frequency I said, not angular frequency. Frequency should be 50. Now for suppose in that expression NAB omega equals to, for suppose E naught, that is maximum EMF, then we can write at any instant EMF induced E equals to E naught sin omega t. So here it is an alternative EMF, so continuously polarity changing, so positive to negative. So middle different changes will be there with respect to time, the EMF will come. So it's clearly indicating that effect. Now we know that omega nothing but 2 pi into mu. So actually omega 2 pi by t, so 1 by t nothing but mu frequency. So omega equals to 2 pi mu. If you substitute instead of omega 2 pi mu, then E equals to E naught sine, instead of omega 2 pi mu into t. So this is the expression for EMF induced by the AC generator in terms of frequency. Now mu is the frequency of revolution of the generator coil. So here how much they are generating, so that is mentioned as a symbol. Now, so how the polarities will change, we can analyze with respect to the diagram. For suppose, so here observe carefully, the coil is exactly coincide to the magnetic field, for suppose, so nothing but angle 0. So if angle is 0, so sine 0 0, then EMF will be 0, so 0 EMF. But whenever it turned to 90 degrees, for suppose here to here, for example, it turned, for example, it is turning, so with respect to our point of view, for example, it is turning like this, anti-clockwise direction, for suppose it coincides exactly, means the plane of the coil coincides with the magnetic field, means magnetic field is in the plane of the coil, or the normal to the plane making an angle 90 degrees with the coil, sorry, 90 degrees with the magnetic field. In that case, here angle between the magnetic field and the normal to the plane, so 90 degrees, so sin 90 degrees value 1, so that is why EMF will be E0, so you will get the maximum value. And again, if you rotate 90 degrees more, so then, so here you can see PQ down. If you rotate 90 degrees and again if you rotate one more 90 degrees, it will be exactly 180 degrees here to here, so that is why that PQ came to the top position. So here to here 180 degrees. So the total angle turn is 180 degrees, sine 180 degrees value 0. So that is why again EMF 0. Next, if you rotate extra 90 degrees, total 270 with respect to the initial position, so means again it will be flat, or the normal to the coil making 90 degrees with the magnetic field, so then again sine 270 nothing but 1, so again EMF, but that is third quadrant, so -1, so that is why EMF will be minus E0, so that is why the polarity changed. Okay, next, if again rotates 90 degrees, if you rotate 90 degrees, the total will be 360 degrees, again you will get the as it is initial identical position, so then again EMF 0, so sine 360 degrees nothing but sine 0, so nothing but EMF 0. The model AC generator block diagram you can see here, so the entire total coil, so we can rotate this one, means we can apply mechanical energy and we can rotate in anti-clockwise direction, and ends of the coil you can see one end is continuously in connection with the brush, first one, or you can say ring, first ring, and other end continuously is in contact with this one, so second ring, and the entire coil is in magnetic field. So in magnetic field, if you rotate this one continuously, flux will change in it, so the change of flux induces EMF, so that polarity sometimes plus sometimes minus, so alternating current will generate, so with respect to that bulb will glow here. So this is the block diagram for AC generator. Thank you.